get one thing straight. Building a star on Earth is hard. So when we talk about nuclear fusion, which is essentially this process of recreating what naturally occurs in stars, we often dub it the holy grail of energy. Not necessarily holy grail in a good sense, the holy grail in the sense that it may never be achieved. So nuclear fusion is arguably one of the hardest and most rewarding problems that humanity can work on. If we succeed, a single glass of seawater can produce the same amount of energy as a full barrel of oil, with no waste. Yet, our innovations in energy today are still focused on renewables like solar or wind, which are awesome but have incredible limitations. You see, something like solar is really just crappy nuclear. We talk about harnessing the energy of the sun, right? Well, with solar, you're just getting scraps of that energy. But with nuclear, you're recreating the source. So what I'm going to try to do today is convince you that fusion is the end game. First, we're going to do a little primer of fusion, what it is, why it matters, why you should care. And then I'm going to go over how I'm building a nuclear fusion reactor in my garage at 17. And then we're going to end up by talking about the bleeding edge of the space, why private millions are currently pouring into fusion startups, and what that can mean in the upcoming years. So let's start from the beginning. What is fusion, and especially what does it compare to fission? So I have 4 squares here. On the left, we have fission, and on the right, we have fusion. Fission is essentially taking a heavy atom like uranium or plutonium and splitting it apart. And when you break those bonds, energy is released. Fusion is taking 2 light atoms like hydrogen or helium and smashing them together. And when you do that, you lose a little bit of mass, more energy is released. Let's further split this up into controlled and uncontrolled. Uncontrolled fission is essentially just an atomic bomb. Controlled fission is what we're talking about when we're talking about nuclear power today. It's what's currently powering all of the nuclear reactors that are converting energy by powering steam engines. Now, fusion uncontrolled is a hydrogen bomb. Fusion controlled, that's what we're talking about when we talk about the future of energy. That's what we're talking about when we talk about energy that potentially has 0 carbon, 0 emissions, 0 greenhouse gases. This is what we're trying to achieve. Now, this is really why something like solar or wind energy don't really stick up to fusion. Solar is limited by the fact that it's essentially just a nuclear reactor, but 100 million miles away and out of our control. Wind is also completely out of our control. We can't control whether it's stormy or whether it's still a peaceful day. Fusion, on the other hand, is potentially near limitless green energy. If we want to talk about replacing fossil fuels, replacing the grid, potentially fighting climate change, going to space, fusion might be our only option. Now, over the past couple of years, governments and countries have poured billions of dollars and their top talent into research in fusion. ITER is an international mega project collaboration between 35 countries, and what they're working on is really researching a type of nuclear reactor called the tokamak, which is this round donut vacuum that you see on the screen. But in recent years, the biggest breakthroughs toward commercial fusion have not been through ITER. It's been through private companies and startups with much less people and much less funding. So if they can do that, then what's the next version? Well, a 17-year-old in her garage with a few $100s. Maybe I took that a little too far, but here we are. So when I first started researching fusion, what I realized is that it's actually quite possible to build a small fusion system that builds up a high energy beam that collides and does fusion. And so what I'm trying to build is something called the Farnsworth-Hirsch fusor. When you're actually trying to achieve fusion, what you need to do is condense your fuel so that it's hot enough and dense enough to actually confine plasma. And stars can achieve by doing this by using gravity through something called gravitational confinement. But on Earth, scientists kind of have to take this into their own hands, and the 2 main ways that they're doing this is something called magnetic confinement and inertial confinement. With magnetic confinement, what we're trying to do is use magnetic fields to confine this plasma, and with inertial confinement, we're using a fuel pellet's own inertia. In other words, its inability to move away fast enough to actually confine that plasma. Now, in our fusor, we're using something called inertial electrostatic confinement, which essentially means that we're using electrostatic field to confine that plasma at the center of the vacuum. So let's break down some parts. First, we have a vacuum chamber. All nuclear reactors have this. A tokamak, as you previously saw, has that sort of donut D cross-section vacuum. A accelerator has more of a twisty-turny one. This is the one that we're working with. And at the center of that vacuum, we have electrical grids, which is where that plasma is going to form. Some other parts, we have a transformer that takes us to high voltage. We have a rectifier that charges the grid. We have a vacuum pump that evacuates the chamber. and a vacuum gauge that measures the pressure. And there's a lot of other components, but I'm not going to bore you with them. And frankly, I'm still trying to understand many of them myself. A lot of this process has really been trying to understand high voltage systems, vacuum systems, and radiation safety above all else. So this is what it looks like, and this is what I'm trying to achieve. That beautiful purple glow that you see in the center is how in low power fusers you have an ion plasma glow discharge. But in high power fusers, basically the ions colliding at the center actually compress the hydrogen enough that they start to fuse. So at this point, you may be wondering, here's a miracle solution. You can build it in your garage. Why aren't we there yet? And if you've been following fusion, you'll understand that the issue is no longer really achieving fusion, it's getting energy out of that reaction. This is something called net energy gain. Right now, the amount of energy that we're putting in is still less than the amount of energy that we're getting out. If there's no net energy gain, then it's not a viable power source. But 3 months ago, at the Lawrence Livermore National Ignition Facility, or the NIF, they actually managed to conduct a fusion experiment with net energy gain. That's the headlines that you've been seeing about fusion. But what does this mean? Does this mean that we're there yet? Does this mean that we're on our way to unlimited clean energy? Not necessarily. You see, when you actually start accounting for the incredibly inefficient lasers that the NIF used in this process, you'll understand that the actual energy gained from this reaction and the system itself is not at all viable for commercial fusion yet. This isn't to say that this is a huge breakthrough, it absolutely is. But the issue is that organizations like the NIF have very different priorities. They are focusing on researching the science behind fusion and how fusion works, but not necessarily how we can get to commercial fusion as soon as possible. And we're solely depending on government organizations to research fusion, then it's safe to say that fusion energy is not going to be a reality for another few decades, which is way too late for the climate fight. Instead, what we're starting to do is turn towards startups in the space who could take us to this dream of commercial fusion. I want to highlight a few of them for you today because they're really awesome. So the NIF isn't the only facility working on researching inertial confinement fusion or laser technology. First Light Fusion is working on a type of inertial confinement called projectile fusion. They were inspired by something called the pistol shrimp, which is essentially this creature that can snap its claws so fast that they create bubbles that collapse to form 4,700 degrees Celsius plasma bursts. A shrimp can do this. And so what First Light is trying to do is essentially recreate this process in their reactors by shooting a projectile at a cube of fuel source. And upon impact, the bubbles in the fuel source burst and they collapse and the fuel compresses to fuse. If they're successful, they're looking at a projectile fusion plant sometime in the 2030s costing less than $1 billion to build. Another startup that I want to look at is Helion, and what they're essentially trying to do is take an approach called direct energy conversion. And what this means is that instead of going through the traditional huge steam turbines, they're looking at harnessing energy directly from the beginning. Now, other organizations may have achieved net energy gain, but it's usually in a format that's hard to use or hard to convert, which is another issue that pops up when we're talking about commercial fusion reactors. By starting to look at electricity straight from the beginning, Helion is taking a huge advantageous leap towards commercial fusion. And then there's Commonwealth Fusion Systems, which is an MIT spinoff that looks at more compact tokamaks. And what they're doing is using superconducting magnets to be able to confine the plasma in a much smaller space. And for scale, their rig is only 2% the size of Inner's tokamak, and they're looking at a power plant sometime in the 2030s. So let me leave you with this. Energy is the currency of our universe. If we succeed in achieving nuclear fusion, we will be achieving the holy grail of energy. Not holy grail in the sense that we may never reach it. Holy grail in the sense that it could save our planet, it could fight climate change, and it could potentially be the future of energy that we've all been waiting for. Thank you.